Welcome to the MOOC lecture series of the RIGHTWEIGHT project of Internet Northwest Europe. Today I would like to discuss the subject of sustainability and recycling of composites. But first, I would like to introduce myself. So my name is Ilse Bruggekaten. I have a background in mechanical engineering and currently I'm working as a process engineer at TPAC. TPAC stands for ThermoPlastic Composite Application Center. We're located in Enschede in the east of the Netherlands. There we're part of the University of Applied Science. So at TPAC, we're an independent innovation, research and development center. Our main focus is to understand thermoplastic composites and all related technologies to process, manufacture those materials. We mainly do that by developing proof of concepts for SMEs, so small to medium-sized companies. We're self-supporting through all our research projects, and currently we have up to 50+ partners. So our focus, cost-effective thermoplastic composites for SMEs. And how do we do that? We do that in 3 main research areas. So processing, automation and recycling. For processing, we mainly focus on the development of cost-effective processes and to integrate those with thermoplastic composites. So for example, we look at existing processes and how can we change them to fit thermoplastic composites, or how can we develop new processes. For automation, we focus on integration of machinery, so can we change a manual process to an automated process, and how can we do that as cost efficient and, well, in the meantime also improve the quality and the producibility. And then lastly, recycling. Main topic of today, but for recycling, we look into the development of new materials, but also the processability of those materials and the design possibilities. This is both for thermoplastic waste as for composite waste. Of course, those 3 research areas in most cases are quite combined, so no research projects only focuses on one, but quite often on a combination of 2 or 3 of those areas. But for today, we have the following agenda. So first I would like to start with some sustainability, and I'm especially focusing on composites. For that I would like to discuss some production, maintenance and energy savings. Then I would like to have a short look at some end of life. So what can we do, and what are our recycling methods available? For that I've selected 3 case studies. Those case studies have been researched at TPAC and a quite recent project we finished. So, for example, a recycled thermoplastic composites access panel part, but also the manufacturing of a cork PLA product and an automotive demonstrator, 100% made out of recycled polypropylene. So to start with sustainability in composites. So again, production, maintenance and energy savings are one of those topics we're going to discuss. The goal for today would be to give an insight in sustainability and an insight in the current state of recycling methods by 3 case studies. But to get a better understanding of sustainability, I think it's good to start with life cycle analysis. So I think most people know what an LCA is or what it would roughly mean, but I think it's good to discuss it in a bit more detail. So LCA stands for life cycle analysis, and this is a collective term for methods used to examine environmental impacts of structures and products. So for example, this method looks into if I would use a polypropylene or a PLA, what are the different impacts it would have, or if I would use an injection molding process, a compression molding process, or something completely different, what is the environmental impact of that choice? In this case, you can split it roughly into 5 sectors. So we start with raw material. Raw material is collected and processed into a product. That product would need to be transported from the manufacturing location to a retail location, and then after consumer buys it, it will start its use phase. If the consumer later discards his product, it will result into waste. So those 5 aspects, those 5 phases, are also the 5 life phases we can distinguish of a product. So, to make an LCA analysis, you would need quite a lot of data. For that you can use LCI, so life cycle inventory. This is a database that includes a specification of environmental impacts per material or per structure. So an LCA, that database, is compiled with lots of care. However, it's still partly based on assumptions. So it's quite important, if you're compiling your LCA, to be aware of that and make the correct assumptions in your case. So to give a couple of samples, what can be expressed with an LCA, I think the most known is the global warming potential. So for example, your CO2 equivalent. But CO2 is not the only aspect that you would have to take into account for your global warming potential. For example, methane also affects this. But there are other aspects you can filter out with an LCA, for example, the human toxicity. So if we look at the image on the right, there are 4 aspects you have to keep into account when doing an LCA. You have a certain goal and scope for your research. You have your inventory, so your database and your values. You're assessing the impact. Those are all intertwined. And in the meantime, you're interpreting those results. So of course, it's possible if 2 people do an LCA, the results might slightly differ. But that's why it's very important to make the correct assumptions and document your findings. But to better understand this, I think it's good to take a step back. So we'll first have a look at the environmental considerations. To do this, I would like to have a look at the total material cycle. So that's the picture on the right. This gives a cradle-to-grave overview. So in this case, raw materials are collected from its natural habitat, like by means of mining, drilling, or harvesting. And they will be processed, so by synthesis or other processing. And we convert materials by purification, so we go from a rubber or fiber to an end product, such as metals, plastics, composites, or elastomers. If we reach that point, we call them engineered materials. With those materials, the production process starts. So a design can be made, manufactured and assembled, and we slowly move on to the application phase. In this application phase, the user uses the product until they no longer need it. So at some point they will discard it and it will become waste. It can become incinerated or it can become landfill and it will be returned. However, there's another option, and that is that the waste is not landfilled or incinerated, but recycled and reused. Then we would reach a more circular construction. So important to know is that yearly 15 billion tons of raw material are extracted every year. Some of those are of course renewable, but not all of them. So how can companies then get an insight into the effects of their chosen materials? The LCA. And an LCA analysis can give an overview of all considerations made for the entire cradle-to-grave environment. So, from material extraction to product and manufacturing, and the use and final recycling and disposal. For this, the company would have inputs and outputs and map them all out. So they look at the energy, the raw materials, what affects them during material production or the product use, and all the outputs that occur there. So for example, of course, your usable products, but also your contaminations of air, water, and your solid waste in the end. So for this approach, it's quite important to have all your variable inputs and outputs mapped out to get a correct and complete overview. Then, regarding composites. In general, composite structures are of various possibilities for low energy design. So for example, you can increase your environmental impact by making your composite structure not out of glass, but out of a natural fiber. So on the image of the left, we have an overview what the impact is of various greenhouse gas emissions, again according to LCA analysis. And natural fibers show a lower emission than their fossil-based materials, so to compare them. So the impact on climate change, for example, glass fiber production is 4.5 times higher than if we would select a natural fiber like flax, hemp, bamboo, or wood. So in general, biocomposites show greenhouse gas emission savings between 10 to 50% compared to their functional, equal fossil-based ones. If you would even include the carbon uptake, our greenhouse gas savings would even go higher, so up to 30 to 70%. then to better understand the importance of using bio-based material, I think we need to take another step back. So in this case, the carbon cycle. A carbon cycle is quite a complex process by which carbon exchanges between 4 main reservoirs. So limestone, plant and animals, biocarbonate dissolved in the ocean, and of course the atmosphere, our CO2. So in general, it's a balanced, or it's supposed to be a balanced process. However, human interactions like burning fossil fuels or massive deforestation affect that balance in a negative way. This means that no longer the photosynthesis or the biocarbonation in the ocean can resolve that imbalance, thus resulting in an accumulation of CO2 in the atmosphere and contributing to global warming. Rebalancing this could be helped by using more renewable materials, for example, bio-based composites. So how to rebalance that carbon cycle then? So it's important to then look at your production technologies and see what your CO2 emissions are. For example, of course there are many ways, but if we would look at composites, if we would use bio-based plastics, we can help rebalance the carbon cycle by reducing our CO2 emission. Then to look a bit closer, bioplastic, so your matrix material, is a renewable polymer. However, not all bioplastics are biodegradable, so those are 2 different things in this case. But then what is biodegradable? So biodegradation is a process capable of decomposition of materials into CO2, methane, water, inorganic compounds or biomass, in which the predominant mechanism is the enzymatic action of the microorganisms that can be measured by the standard test. So in a specific period, reflecting available disposable conditions. So what are those parameters then? To determine what influences biodegradability, we look at, for example, the humidity, temperature, pH, but also presence or absence of oxygen or supply of nitrogen. Then there are a couple of standard tests to determine the level of the biodegradability, and those are summed up on the right. So we could look at the oxygen consumption by means of microbes, change in mechanical properties regarding the molecular mass, or look at weight loss measurements, so determining the residuals of the polymer. So, in general, we can split biodegradable polymers into 2 types. The first one are polymers that instinctively are biodegradable, so whose chemical structures enables direct enzymatic degradation, like starch, cellulose. And in the second category, we could say polymers that undergo photooxidation or thermooxidation upon exposure to UV or heat. In the overview below, we have 4 main classifications. So biomass products, or something generated from like microorganisms, biotechnology, or petrochemical products. These then again can be split into more detail. For example, those biomass products. We have starch, ligno-based, or even plant or animal-based. Then we have generated by direct biosynthesis from microorganisms. The biggest group is the PHAs, or looking at the biotechnology, of course, the most common and most known are the PLAs. And for the petrochemical, we have PCLs, but also other biopolyesters from the more conventional syntheses. So, as mentioned before, composites have many advantages. For example, maintenance and repair. So again, to go back to the sustainability, if you can use a product longer by means of good maintenance or repairing the product, we would not have to discard it as easily. So for example, we have composite structures in general, they require a little bit less maintenance if we would compare them to their steel or wood counterparts. So for quality, they're a little bit higher and their lifespan could be a bit longer. For example, the corrosion-resistant composites, they require 44 to 65% less maintenance if you would compare them to aluminum. And in constructions and infrastructure, they're a bit more durable. The example on the right is from a composite decking compared to a wood decking. So in this example, the maintenance for the composite decking would be sweeping, maybe washing it a bit, and the same could be said for the wood decking. However, the wood, of course, would have to be sanded, sealed, stained, and painted over time. But whereas in the composites, that would not be the case. Then looking at the repair. In general, repairing composite structures is a possibility. The damaged part would have to be removed, and if we're talking about thermoset materials, it could be executed on site by means of a hand layup or a pre-pack. However, for repairing, still lots of research is being executed, and the question is often if it's cost efficient enough to repair the product or it's replaced. Depending on the application, you could recycle the material or repair it on location or off location. So, as already mentioned before, composites are lightweight, so lightweight materials, resulting in a lightweight design that would improve our energy efficient structure. So I have 3 sectors as an example: transport, automotive, and industrial. For transport in general, we can say that the energy consumption is related to the weight of the material used. Thus, a heavier load, a heavier truck, for example, would have more resistance on the road, or a heavier boat, more resistance on the water, and it would reduce in a higher price. If we could save the weight there, we would reduce our resistance, and we could improve it there. Automation of automotive is the same. In automotive, a lightweight design plays quite a big role in the fuel consumption, but also in the payload. And for industrial applications, it's depending more on the production rate. So if we would increase our use there, machines or robots would be a little bit lighter and stiffer, and the production rates could go up. So eventually, the freedom of geometry and the lower weight offered by composites prove a direct energy saving through aerodynamic designs. So this concept brings us closer to the idea of eco-design. So ecological design or eco-design is an approach to design products and services that give special considerations to the environmental impacts of an entire life cycle of that product or service. So in definition, it's said that the process of integration environmental considerations into lightweight design and design for circularity with the aim of products through their life cycle. So it can be split into 2 main categories if we're looking for thermoplastic composites. The first one is the lightweight design, and we're looking at reducing emissions. It can be done by 3 main ways. So by integrating structures, so we're reducing our amount of joints and thus our weight of our product. By looking at a structural efficient way of using materials, so only placing your fiber reinforcement on the locations you need it, so removing the additional mass, and by optimizing our structural design in general. The second point would be to design for circularity. In this case, we mainly focus on recycling. It can be mechanical or organic recycling. An example that was executed at the TPAC laboratory are those automotive demonstrates on the bottom corner. For example, those were made from glass fibers with recycled polypropylene, or recycled PET with PET fibers again, and flax PLA to be more sustainable. So we have seen composites in many applications, but of course the question now would be, what do we do at the end of their lifetime? How do we recycle them? So we can split composites in general into 2 categories, thermosets and thermoplastics. Both have still quite a lot of recycling challenges, but they're quite different. Of course, the thermosets are more known to be used and mechanical recycled or chemical recycled, whereas thermoplastics, they could be reheated and reshaped again. So there are 2 different scenarios to look at. But in general, it can be said that composites are still quite difficult to recycle because they're a multi-phase material. This means that we're combining 2 types of materials, so fibers and a polymer, and it's quite difficult to separate them again. So one of the most typical recycling techniques we see quite a lot is mechanical recycling. In this case, most often the material is shredded or grinded, and components are reduced in size quite drastically, so that results in short-length fibers. Those short-length fibers, depending on how much you grind them, they could again be blended with polymetric matrix, and by means of different molding techniques, so extrusion or injection molding, they could be used in a new product. However, there's also another option. We could look into the separation of matrix and fibers. So if the matrix would be volatilized, the fibers could be recovered and reused again. However, in this case, you're losing your matrix material. That's nowadays becoming more and more valuable. Other option would be to try to recover our matrix as a monomer. But in this case, we might be damaging or losing our fibers. So it's something to take into account what you want to recover and how we are going to work with that. But in general, we're speaking of a reduction in fiber length. Because if we're shredding or grinding, or even if we're removing our matrix material, our fibers are no longer continuous and will be reduced in size. Thus, our mechanical strength is reduced. Then the question would be, how are we going to deal with that? So for that, I would like to discuss in total 3 case studies we've executed at TPAC as an example of possible recycling techniques. So the first case study, talks about recycled thermoplastic composites in an access panel. So in this case, we have been working on an access panel that has actually already flown, so it has been tested. But it was part of one of our larger projects, TPC Cycle. In this project, the goal was to develop a recycling route for high-end and high-volume markets. Objective would be to retain high mechanical properties we would have and reduce environmental impacts, still at an affordable cost. So how would we do that? We started by developing our own recycling route. So the material would be collected, could be trims, could be damaged products or production waste. They would be reduced in size, depending on step C, the size reduction would be bigger or smaller. And those shredded flakes, in our case, were then used in a low shear mixer. That low shear mixer heats and mixes the material, if required, with additional matrix material. And a hot molten mixed dough comes out at the end. That material can immediately be placed in a compression mold and can be molded into your desired shape. After cooling, it can be released and you immediately have your neat product. So no additional manufacturing would be required. Other option, of course, is if you're not working with a low shear mixer, you could go for an extruder. If you're working with a bigger die, you could go for a profile. Or if you would grind the flakes smaller, you could go for more of an injection molding compound. But in our case, we mainly focused on the line process where we would compression mold the product that would need no more maintenance after it was released of the mold. And how did we then do that? So our goal was to create multiple demonstrators, and one of them was the access panel. In total, it took less than 2 years to go from scratch to a flight test. So it was a complete in-house development. And it was, well, we think the world's first 100% recycled demonstrator that has been flight tested. But what does that do for the savings? So if we would compare it to the current carbon epoxy hand layup, then we are saving roughly 80% in CO2 emissions already. Weight-wise, we're saving 9%. Because of the process, we can integrate the rips on locations we want and thus using less material and becoming a little bit lighter. Cost-wise, we're even saving 70% compared to the current hand layup. To further introduce it, I would like to share a short video about the entire recycling process. Then for a second case study. So for a second case study, we looked at manufacturing cork and PLA products. So both cork and PLA are bio-based materials. Actually, cork is a renewable, biodegradable, and, well, eco-friendly material. And it's quite nice to combine with PLA. So in our lab, we have examined extrusion or compression molding of cork. But the bigger question was, if then the cork product has gone through its life cycle, can we then recycle it at the end again? So for that, cork PLA products were shredded, compression molded, and reshaped into new products. And actually, they could be manufactured again with the same processes. So again, extrusion or compression molding. However, also some investigation has been done to reducing the processing time. So for example, by softening the product by heating steps or ventilated oven, and then shaping the softened product into a desired shape, the processing time could be lowered quite a bit. And then our final case study. So an automotive demonstrator. In this case, it was part of one of our projects, the FiberDeck project, and we have been looking at upcycling waste plastic for high-value continuous fiber reinforced composite applications. In this FiberDeck project, the main question was, how can TPC reinforced products be produced entirely from recyclates in series, and to what extent is it possible at a still competitive cost? So in that case, we had a look at waste streams, additives and fibers, and how to combine them into a tape. So glass fiber, reinforced tape, or flex fiber tape. Those tapes could then later be processed into different types of inserts, and by combining inserts and recycled material again, we would like to work through a demonstrator. So in this case, we selected a generic typical automotive part, seen on the right, and we tried to combine different types of fiber inserts on specific locations. So in this case, we have an edge insert completely around the part. We have protruded rods in our ribs, and we have a woven or an organo sheet, for example, in the part completely. Then it would be overmolded, and all the greener parts are then injection molded onto the demonstrator. So in this case, we would have 100% out of recycled plastic a part. So only addition would be to add virgin glass fibers, for example. So to sum it up again, a tape production, 3 types of inserts, and then our demonstrator, all combined on an angle insert machine. This has been done with quite a lot of in-house developments. So the first step would be we produce the tapes, but then we need to make a woven material. And we were quite looking to how can we weave those tapes without doing it by hand, but still automating the process. So in-house, a weaving setup was developed where different kinds of woven materials could be created. So in this case, it's weaving the following setup. And if you would combine 2 of those layers with a little bit of additional granulate, you would have a 2 mm consolidated plate. The plate can then be milled to size and be used as one of those inserts. The other step would be to, for example, 3D print the edge insert. So for the edge insert, we first have done tests on a MOOC robotic arm, where it prints around a mold to ensure we would have a certain rectangular insert. However, recently we also have looked into creating those inserts on a different and perhaps quicker method by winding them. The last step is, of course, those protruded rods. Those protruded rods are created by pulling the flat ribbon-shaped tape through a die to result into 2 mm round filaments. Those filaments are actually used on the robotic arm as well, but we could also place them into our demonstrator. In total, I would get the following in the demonstrator. So we started with a mold and woven TPC material. It's on the complete back of the product. We would add rib stiffeners by means of protruded rod, and an edge stiffening insert 3D printed with a robotic arm. Those would all be placed inside the mold, the edge and the inserts first. Woven material will be heated by means of infrared and moved by a robotic arm to go in the mold as well. The mold will close, and then the injection molded ribs and edges are added to create the full product. And that was already my last slide of the lecture. So I would like to thank you for joining the MOOC classes, and I hope this training helped you. For any questions, don't hesitate to contact us via info@ThermoPlastic composites. Thank you.